talking about T-duality and killing horizons. So please.
Okay, thank you, Gabriel. So first of all, greetings from Liverpool to everybody in attendance. Special thanks to Gabriel, Suresh, and possibly other people in Lisbon for organizing this. And I'm very happy to have the opportunity to talk here. What I'm going to speak about is based on work with several collaborators. There's my long-term collaborator Vicente Cortés, who's a differential geometer. Oscar Schiller is his PhD student. And some work was done with Maxime, my previous PhD student, and now work with Matas, my current PhD student. So what's this about? A non-degenerate killing horizon is a hypersurface in space-time where the killing vector field turns from being space-like to being time-like. I've given you here an example line element which realizes this, provided that the function f of r has a simple zero at some point r star. It's not the most general such line element. I have chosen it in such a way that on the side where the killing vector field is time-like, the space-time is static rather than stationary. So therefore, I forbid that it rotates. But it includes Schwarzschild and non-extremal Reisner-Nordström as examples. Now, if we were to apply the Buscher rules to such a background, then at the horizon, we would be dividing by zero. So the Buscher rules break down at killing horizons. And very early, it was observed that the T-dual of a killing horizon is singular. And you can check that's not a coordinate singularity, but there's a genuine curvature singularity for this class of metrics that I have shown you. Here's the outline of my talk. I will first talk about T-duals of killing horizons from the perspective of Riemannian geometry. This will then motivate attempting to developing a perspective in generalized Riemannian geometry. These two threads will not quite meet each other. So in the outlook, I will indicate how this is supposed to get together in the future. So here's part one, the Riemannian perspective. As a starting remark, the term T-duality is used with a variety of different meanings. One very strict meaning is that it's an exact symmetry in string perturbation theory, valid order by order in the genus expansion, being a strict identity for partition functions. And this requires that the killing vector field acts with compact orbits. So we would need to compactify space or time for this to apply in the strict sense. The term T-duality is also used more generally for a solution generating technique, which I can apply in supergravity or even in non-supersymmetric gravitational theories, which works by dimensional reduction, field redefinition, and lift. Given then a solution of one theory, I can apply this technique to get a solution either of the same theory or of a different theory, and this works irrespective of orbits being compact or non-compact. It also reflects in common imprecisions on our language. We tend to say type 2a and type 2b superstrings are T-dual, where in the strict sense, they are the two opposite ends of a one-parameter family on which T-duality acts. We also tend to say that Dirichlet P-branes are T-dual to P+1 or P- branes, which again is to be understood in the sense of solution generating. Anyway, I'll be working in this part in the loser setting, where the killing vector fields act with non-compact orbits, and I won't make any explicit claims about physical equivalence. I will just ask what happens at the image of the initial solution at the points where interesting things happen, like the horizon, but also the singularity, if we were to assume that we look at Schwarzschild or Reisner-Nordström. I will still want to have an embedding of what I'm doing into string theory. And my starting theory will be Einstein-Maxwell. If I apply T-duality by this reduction oxidation procedure, I will end up by as you will see in Einstein-Dilaton axion gravity. Now this can be embedded into n equals to 2 supergravity, minimally a supergravity together with one meta-multiplet, a hypermultiplet, which is in fact the universal hypermultiplet. This in turn sits in n equals to 8 supergravity, which we can obtain by torus reduction from type 2a or type 2b superstring theory, which are T-duals of each other. However, n equals to supergravity with one universal hypermultiplet is also the universal sector of any type 2 Calabi-Yau threefold compactification. Universal in the sense that this is what remains if I freeze in all geometric moduli and all Ramond-Ramond moduli which sit in the same supermultiplets. Okay, now I will also want to do T-duality where the killing vector field is time-like. And in this case, let's start from the top. In 10 dimensions, if following Hull we apply time-like T-duality, we will get from the standard type 2 superstring series to the exotic type 2 star superstring series. And then if I trace this downwards, this creates kind of splitting of all my theories into standard versions, say of Einstein-Maxwell or of Dilaton axion, and twisted versions which differ by certain sign flips. Generally, the type 2 star theories are distinct from the standard type 2 string series by certain phases in the partition function. Now, the status of these type 2 star theories is, I believe, ultimately unsettled. They have various exotic properties like the sign flips, which lead formally to negative kinetic terms. And in fact, one of my long-term objectives is to learn more about the status of these theories. For the time being, this is just the formal framework in which I have to work if I want to allow T-duality on both sides of a killing horizon. But if you are a radical skeptic on these things, at least half of my talk will still make sense because you can simply stay on the side of the killing horizon where the killing vector field is space-like and T-duality works in the usual way. Okay, now for reference, here's the bosonic sector of n equals to 2 supergravity together with a universal hypermultiplet. So it's essentially Einstein-Maxwell plus 4 scalars, which, depending on whether we have the sign flips or not, parameterize this or that symmetric space, which, if you care for n equals to 2, supersymmetry is quaternionic Kähler, the standard case, and para-quaternionic Kähler in the other. This is written here in the Einstein frame, which is well adapted to the supergravity multiplet structure, but is not quite adapted to T-duality and also to tracing what comes from the NS and RR sector if we embed into type 2 superstrings. So for this, it's better to go to the string frame, making conformal change of the metric and also reconverting the universal axion back into a B field. And then we see here in the first time the universal NS action, which takes the same form in any dimensions. And then we have further terms of those fields which descend from the Ramond-Ramond sector. We then have re-derived this context by dimensional reduction, field redefinition, and lifting the Buscher rules. That's why I call them 4D Buscher rules. Of course, the NS sector is completely universal, so we get the usual, but it's a nice check for accurateness of your computation. The expressions given here in red are those fields which are the actual players in my solution. We start out with a diagonal metric, and therefore we don't generate a B field, but by the usual shift, we create a dilaton, even if we start in a situation where the dilaton was not present or was constant or truncated out. The Ramond-Ramond sector is, as always, non-universal, so that's why we had to do this rederivation. The Maxwell field, in principle, gives you 2 axion-like scalars, but only the one in red really appears in our solution because for the blue guy, the expression vanishes on the background of our solutions. And as you see here, we have always traced what happens if you have one of those twisted series where you have some sign flipping kinetic terms for reference. The case study that we carried out was for the planar version of the Reissner-Nordström solution, for which I give you the line element, the Maxwell field. And here's the function which modulates this. Essentially, you drop the constant factor, which normally makes the solution asymptotically flat. It's an electrovacuum solution, meaning the Ricci scalar is identically 0. It has a horizon and has a curvature singularity. Compared to the spherical version of Reissner-Nordström, it's kind of inside out in that the region between singularity and horizon is static, whereas outside the horizon, the Killing vector field becomes space-like and the solution becomes dynamic. Indeed, the solution is best interpreted as a cosmological solution. After maximal analytic extension, it becomes a bounce, interpolating between a contracting and expanding Kastner solutions with a bounce caused by two branes, which correspond to the singularities, one of which we see in the patch currently under consideration. This configuration lifts up, so these singularities map up to branes. In fact, this lifts, if we choose an embedding into type 2a, into everybody's favorite triple intersection of D4 branes sprinkled with D0 brane configuration. Now here's the T-dual solution. We have a line element. We have, as I said, a dilaton that we generate. And from the Maxwell field, we get one of those Ramond-Ramond axioms. Strictly speaking, this is not valid at R equals to R star, where the Busher rules break down. And if we look at our embeddings, then in the static region, we would go by T-duality from type 2a to type 2b star, one of the exotics. And outside, where the Killing vector field be used for T-dualizing the space, like we would go to type 2b instead. I will call the place R equals to R star an interface because it's somehow where type 2b star and type 2b potentially meet. But we want to understand what the nature of this locus really is. So here's a summary of the behavior. R equals to 0 was the original singularity. And that's again mapped to a singularity. And it's a singularity in the sense of Ricci curvature, so the Ricci scalar diverges at this locus. The same happens at the image of the horizon, irrespective of whether you approach it from the space-like or from the time-like Killing vector field region. The Ricci curvature will diverge if you approach this locus. So we are a bit worse off than before. Before we had a singularity in the horizon. Now we have two singularities. We have created a dilaton, which goes to minus infinity at the image of the singularity and at plus infinity at the image of the horizon. Now, where does it happen? Where the distance in moduli space is infinite, but the distance in space-time turns out to be finite. So let's look at the T-duals of our special loci in the original solution. The T-dual of the curvature singularity is at the point R equals to 0. Ricci curvature diverges. The dilaton goes to minus infinity. This means four-dimensional string coupling goes to 0. Now we've embedded this in such a way that all geometric moduli are frozen. Therefore, 10-dimensional string coupling goes to 0. Taking this limit at fixed Planck mass means string tension goes to 0. This would indicate that at the locus R equals to 0, tensionless strings will appear. This is consistent with the swampland conjectures, which state that if we go to infinite distance boundary in moduli space, we should always expect a tower of states becoming masses at exponential rate. And by the emergent string conjecture, this should be either Kaluza-Klein tower or tensionless strings, and Kaluza-Klein tower is ruled out in our case because all geometric moduli are frozen. We can try to play the same game at the T-dual of the horizon, but here the dilaton goes to infinity, and therefore the string coupling goes to infinity, so we run into a strong coupling regime. Now, if I assume that an S-dual description exists, then this is a weak coupling regime of the dual theory, and where the inverse coupling goes to 0. And then I would have strings getting tensionless there that are dual to whatever my fundamental string is. Strictly speaking, in the context of 4-dimensional n equals to 2 supergravity, there are only a few special models which have S-duality, but we can embed into n equals to 8. Moreover, as Chris Hull pointed out when I gave a talk about this in Imperial, he took the point that at least microscopically, everything would underneath be 10-dimensional, and I should be confident in applying S-duality. In any case, if you accept these swampland conjectures, since we have frozen all the geometric moduli, the appearance of tensionless strings is the only allowed scenario which can happen. And then the question reduces to what kind of tensionless string we are creating at this limit. And well, if we take it with the standard S-dualities that we have in type 2b, then what is tensionless at r equals to 0 are fundamental type 2b star strings. And at r equals to infinity is the duals of, depending on from which side I'm coming, what is a fundamental string in type 2b star, which is conventionally called the E2 brane. And for the conventional type 2b string, this would be the D1 brane or D string as the S-dual version of the fundamental string. So that's what one can say. Then Adriana Macredo kindly pointed out to us that we could also phrase this in the language of dynamical cobordism, which is related to the swampland cobordism conjecture. So this is concerned with situations if you are within string effective field series and something happens which is at infinite distance in modular space, but sorry for my misspellings here, but at finite distance, I think the F got misplayed, at finite distance in space. Then, according to the literature, there are two allowed scenarios. One should have a true end of space-time, a wall of nothing along the lines of Witten's bubble of nothing solution, so a cobordism to nothing or a smooth capping off of space-time, or domain-like dynamical transition in interpolating cobordism. So what is the status of this type 2 star interfaces is an interesting question. That prima facie we have run in Riemannian geometry just into a singularity. So the question is, can we say anything more about it? So that's why we got sidetracked into generalized geometry, because we were aware that in the literature on double field theory, there were statements that T-duality should actually work at horizons, and that the dual geometry should actually be well defined in the double field theory setting. In particular, this paper here by Mohaupt and Park looked at precisely the type of line elements that we created by applying T-duality and said that these were actually, in a sense, generalized coordinate singularities of doubled diffeomorphisms. Another way we came also, from a mathematical perspective, to this same idea that T-duality should actually work also if the killing vector field becomes null is the following. In generalized geometry, as is done by mathematician, T-duality is called topological T-duality for a reason, because it's not a geometrical, but a topological construction, which you can make without reference to a space-time metric. The space-time metric, or then the generalized metric, is then a geometric datum that you put on your manifolds after you have constructed the T-duality map, and then you can push it through the map and get an answer. And from this context, it seemed a bit surprising that T-duality should just stop to work because the killing vector field becomes null. Now, in further reading of the literature, we found that there are various approaches to curvature and the double field theory and generalized geometry literature, but we think it's fair to say that the theory of curvature invariance and related things like geodesics, the concept of a singularity, the very concept of completeness or incompleteness has not been developed in the same way as it is known in Riemannian geometry. And we will see that there's reasons for this. But our conclusions was then that we should take a step back and revisit the issue of generalized connections and their curvature. And we did this in the context of generalized geometry because half of the collaboration was mathematicians who more easily relate to this kind of framework. Now, before I go into this, I would explain the kind of perspective that I'll be taking on generalized geometry in this part of the talk. It's based on the following observation, which I believe originally dates back to Siegel. If we take the universal NS action in any dimension above 4, then these are actually generalized Einstein equations, or more precisely generalized Ricci flatness equations, and you can define new objects, a generalized Ricci tensor and a generalized scalar curvature, whose vanishing is equivalent to the field equations for the 3 fields, metric, B field, and dilaton. Well, to see that there are actually 3 field equations, note that this generalized Ricci tensor, as I've written down, has an antisymmetric part whose vanishing is the field equation for H, or for the underlying B field. Okay, now, therefore, there's actually 2 perspectives that we can take on generalized geometry. The one that I was used to is generalized geometry is, in a sense, space-time seen by a closed string, or more precisely by the universal zero modes encoded by the NS sector, and the way to make T-duality manifest. But we can take a somewhat broader perspective, which my student Matters like to call generalized relativity. We can focus on that what we are doing is combining diffeomorphisms and B-field gauge transformations into generalized diffeomorphisms. And this allows us to write all equations of motion as generalized Einstein equations. To paraphrase Einstein, what we are doing this way is converting wood into marble by taking stuff that is normally considered matter and put into the energy momentum tensor and move everything else to the geometric side of the equation and absorb it in a generalized form of geometry. Now note that this idea makes sense without reference to strings, supersymmetry, compactification, and even T-duality. The minimal example is just 4-dimensional axion dilaton gravity. In this part of the talk, I will take this generalized relativity perspective, but I will come back to T-duality in the outlook. Now, as I said, half of the collaboration was mathematicians, and we ended up to first write a mathematics paper. So in order to explain our results, I feel I should explain the context. So I will now spend some time of reviewing how generalized geometry is done by mathematicians, or more precisely by what you might call the generalized Ricci flow community based on the book that I'm citing here as the main reference. Of course, all these things have independently and often earlier also been discussed in the physics literature, in particular double field theory, which is slightly different setup, but is this kind of language that we use in the paper and which I will use and therefore review here. And of course, I won't be able to give all the details, definitions, and axioms, but what I will try is to give you a narrative which shows you what are the similarities with Riemannian geometry, but also what is different in this generalized Riemannian geometry setting. Okay, so the buzzword here is exact Courant algebroid, so let me explain this. In the generalized geometry approach, space-time is not doubled itself. It remains as some n-dimensional manifold, which we think of as space-time. But what is augmented is the tangent bundle. It is replaced by an exact Courant algebroid, which we can think of concretely as tangent bundle plus cotangent bundle. Good. And then there's the following data that we need to acquaint ourselves with. The first is called the anchor map. That's a projection of this generalized tangent bundle to the ordinary tangent bundle. And the function of this is that it allows us to differentiate functions along generalized vector fields. So generalized vector fields is something that we can think concretely of as sums of vectors in one form. So we can then, and here's written concretely in this concrete realization, we can take directional derivatives of functions along generalized vectors. Second, since vector fields in one forms can naturally be paired, we have a canonical scalar product or metric of neutral signature, which is denoted by this kind of bracket here, and which is given there. And finally, there is a replacement for the Lie bracket, which is the Dorfman bracket, or twisted version thereof. An important point about this is that it is not anymore antisymmetric. The symmetric part is controlled by a certain axiom that I don't write down explicitly. It's not arbitrary, but a controlled deviation from the antisymmetry of the bracket. But like the Lie bracket, this Dorfman bracket gives us the concept of a generalized Lie derivative, and therefore of a generalized infinitesimal diffeomorphism, and that's where diffeomorphisms and B-field gauge transformations have been unified. If you work this bracket out, or if you present this bracket concretely in terms of this decomposition into vectors and forms, then this term here is the standard Lie derivative or Lie bracket between vector fields, but you also get a form part, which this is called the twisting, also involves this reform H. Okay, so what one then introduces to a generalized version of Riemannian geometry is a generalized metric. This can be viewed in two ways. One way, it's a mapping from E to E, which squares to 1, and which is symmetric or self-adjoint with respect to the scalar product. This, therefore, introduces an orthogonal decomposition of E into two subbundles, E plus and E minus, and these will play a big role in the following. There's a corresponding symmetric tensor, which I can get by slotting in this endomorphism into the scalar product. And this is the object which then can be related to a metric and a B field on the underlying space manifold by a formula that I assume you have seen before. What I would like to note here is that we work with a space-time metric of general signature. Mathematics literature sometimes restricts itself to Euclidean signature, in particular if they are studying generalized Ricci flow. But for us, of course, it's important that we work in indefinite signature, and then one has to be a bit careful with the mathematics literature, because some lemmata and theorems are proven for Euclidean signature only and may not apply if the signature is general. Now, where's the dilaton? So the dilaton is encoded in this setting by a so-called divergence operator on E. So divergence operator is a first-order differential operator, which maps generalized vector fields to functions. Here I've given the expression what happens if you multiply the argument by an additional function. If you try out to pull the function, you produce a term where the function is differentiated along the vector. And this term is precisely what makes the difference between a differential operator and a tensor field. The tensor field does not have such a term. You can pull out functions without them getting caught by derivatives, or in mathematical terminology, one has C infinity linearity and not only linearity in the argument. Now, if I take two such divergence operators and take the difference, then this non-tensorial term cancels out. So the difference between two divergence operators is a tensor field. More precisely, it's a generalized covector, but I can write it using the scalar product in terms of a generalized vector field. So the difference between any two divergence operators is simply a generalized vector, and this is how I can parameterize the space of all divergence operators. Now, still, where's the dilaton? Well, the dilaton comes into the game if I compare my given divergence operator with a particular one called the metric divergence operator. So the metric divergence operator of a generalized metric G is just the same thing as the Riemannian divergence operator of the underlying space-time metric. And so now we have a way of comparing any divergence operator to this standard one. It will often be convenient to decompose the generalized vector, which parameterizes our space of divergence operator, into a vector part and a form part. And the setting that we have in supergravity corresponds to the case vector is 0 and one form is exact, and then this function here is the dilaton. So observe that it is mathematically, we have here the option to generalize the dilaton, and therefore I will refer to E also as a generalized dilaton. And we will see that one particular instance of this has appeared in the physics literature already. Okay, now we want to have generalized connections. So I call generalized connections because I will now want to differentiate not only with respect to vector fields, but with respect to generalized vector fields. Otherwise, it has the same properties as a covariant derivative. In particular, it's tensorial in the first argument. I can pull out functions, but it's a differential operator in the second argument. From the beginning, it is required that a generalized connection on a exact coherent algebra is compatible with the scalar product. This is this property here, and this then defines an O and N structure by restricting the types of frame rotations that we allow to be compatible with the scalar product. Now, if I have a connection, I will want to have a torsion tensor and a Riemann tensor. So this is reviewed here. I treat these tensors as multilinear forms, which means that I completely contract them in every available slot, or if you like, index, with generalized vector fields, and then I look at the resulting functions that I get by saturating the tensor completely by contraction with arbitrary generalized vector fields. So torsion is, the role of torsion is to compare the antisymmetric part of the covariant derivative with a bracket. But here we run into a first difference with the standard Riemannian setting because the bracket is no longer antisymmetric. In fact, this black term turns out to be non-tensorial, but you can add an improvement term to make it tensorial. Similar story for the Riemann tensor. Riemann tensor should measure to which extent covariant derivatives don't commute. Here one needs to do two surgical operations. The blue term imposes pair exchange symmetry, and the red term cancels any remaining non-tensorial terms. Now, if you want to check yourself that this is a tensor, what you would have to do is you slot in an additional function in any argument and check that you can pull it out. Of course, then you need to kind of unpackage the covariant derivatives and so on, which is a bit lengthy but straightforward. Anyway, now, can we have Levi-Civita generalized connections? Yes, but we get more than we ask for. So what we impose normally for Levi-Civita is we say we want that the generalized metric is parallel and the torsion tensor is 0. This turns out not to fix the connection uniquely. Now, that might be expected because we also have to take care of the dilaton, right? So we should fix the divergence operator. So I'll take the divergence operator of my generalized connection and require that it is equal to some prescribed divergence operator. This still doesn't fix the Levi-Civita generalized connection completely. So we have a whole family of them. In the second part of the slide, I summarize what the allowed changes are, which preserve all these properties. So here we have a difference between two connections. Difference between two connections is a tensor. And there's three conditions. The blue condition in plain language means don't mix E plus with E minus. So if you would write S with indices, it would only have E plus indices or only E minus indices, but no mixed components. If we want to preserve torsion freeness, there's a cyclic identity for this difference tensor, and preserving the divergence operator is tracelessness when we contract the first and second slot on this tensor. So these are the issues that we have with curvature in generalized geometry. The Levi-Civita generalized connection is not unique. One can still do lots of things. For example, the equations of motion only involve the so-called generalized Ricci tensor, and the generalized scalar curvature, which are independent of this choice. So these are, as you will see, certain contractions of a generalized Riemann tensor, and one can check there that any difference tensor drops out. But in general, it does not. Similar, the literature on Ricci flow can happily live ignoring this issue. However, if some components of the Riemann tensor depend on the choice of connection, then we can't have a systematic theory of curvature invariance, and therefore no clear concept of what is a singularity. Take, for example, Schwarzschild. Schwarzschild is Ricci flat. If I embedded no B field, no dilaton, so generalized Ricci tensor and generalized scalar curvature will vanish identically. Now, in Riemannian geometry, I can, of course, detect that the Schwarzschild solution has a singularity by computing the Kretschmann scalar. But is there a generalized version of it? Well, no, or maybe. We'll come back to this point. Okay, this was so far purely review, but now at some point we made the following observation. While generalized Levi-Civita connections are not unique, there is at least one canonical choice. Here, canonical or natural, in the way mathematicians use it, means that we can construct such a connection without making use of any additional data. So you give us a generalized metric and divergence operator, and we give you a completely determined Levi-Civita generalized connection. And since this does not depend on any arbitrary additional data, the curvature invariants that we compute in this way are invariants of the geometry and hopefully of the underlying physics. So how does this work? So the first step is to construct a generalized connection which is metric, meaning that the generalized metric is parallel. Now, there's a distinction between so-called mixed and so-called pure components. So the mixed components are those where I differentiate something, where I apply the derivative to something which is, say, an E minus, and I differentiate in the direction of E plus or the other way around. It turns out these are completely fixed to be given by the bracket for any generalized Levi-Civita connection. So they are not the problem. The problem are the so-called pure components. But we can find a metric generalized connection by, in a sense, lifting the Levi-Civita connection, assuming that we are given a metric on G. This can be done using the anchor maps that are introduced. And what we are using here is that, assuming that we have a metric G on M, one knows that if we restrict the anchor map to either E plus or E minus, it becomes an isomorphism. So we can, in a sense, lift the Levi-Civita connection to define the pure components. This connection still has torsion, but now we can apply a well-known trick in this business. The torsion tensor is itself a legitimate difference tensor. So by adding a suitable multiple to a given connection, we can eliminate torsion, and we get a torsion-free and metric connection. And then we can compute its divergence operator, and this turns out to be the metric divergence operator. So in a canonical way, we have found a connection which is metric, torsion-free, but it has a fixed divergence operator. Now we would like to generalize it to also have in a canonical way such a connection with an arbitrary prescribed divergence operators. And but I told you, any two divergence operators differ by generalized covector, so we have to give you for any covector a unique difference tensor which does the job. And this is possible, and for details I refer you to our paper. Afterwards, we then discovered that the connection we found coincides with one which had already appeared in the literature, at least once. I should say that in this literature, there was a lot of parallel work in various communities and sub-communities, often not aware what the other side was doing. So that makes it a bit complicated here. And one often seems to find rediscovering what other people already realized. But I think what we realized is we give, first of all, a new construction of this connection, which is conceptually clear, which makes it clear that, that this is a canonical construction, and which we will also agree is rather straightforward. Okay, this said, now the bulk part of the work in our paper was then to take this connection now to compute all curvature components, all components of the Riemann corresponding Riemann tensor, and then also to look at all the tensors which you get by contraction. So first, I give you here the generalized Riemann tensor in the case where the dilaton is switched off, metric divergence operator, and I give you the interesting components which are the pure components. So I've slotted here in either generalized vectors which are all in E plus or all in E minus. These are the interesting components because these are the ones which depend on the connection. But as you can see, with our canonically chosen connection, we get something which is the Riemann tensor, and then various terms which are quadratic in the three form with contractions which I've indicated here. We have, of course, also reworked all the other components and where applicable, checked that what we get is consistent with the literature. Now, what happens if I switch on a generalized dilaton and change my divergence operator by an arbitrary generalized vector? Well, the answer is rather complicated. I give it here for illustration. It doesn't make sense to go over this term by term here. But what I will do now is to talk about the tensors that you get by making contractions. And at some point, I will also give you formulas in index notation, which will give you hopefully some intuition of how these dilaton terms then work and how the resulting tensors work. So we take now a contraction in one pair of indices, if you like, and there's only one non-trivial inequivalent single trace object that you can construct, and this is called the full generalized Ricci tensor. So we are taking here the trace in the first and third argument. And we do the trace using the scalar product. If you would take the trace with the generalized metric, you would get identically 0, by the way. Okay, now this is a full generalized Ricci tensor, and called full because A and B are arbitrary generalized vectors. So we can have pure components or plus components, if you like, minus, but also mixed plus minus and plus minus. The mixed components are independent of the choice of a Levi-Civita generalized connection, and they comprise what is known in the literature as a generalized Ricci tensor without calling it full. And this is the object which appears in the supergravity equations of motion. But as we see, the pure parts of the full generalized Ricci tensor also play a role. Now we come to double traces, which give us curvature scalars. And there's, in fact, 2 of those, because I can trace the generalized Ricci tensor either with a generalized metric or with a scalar product, and I get 2 non-trivial expressions. The generalized scalar curvature is well known. This also appears in the supergravity equations of motion, but the second scalar invariance that we give here is new. But as you see, it only depends on the generalized dilaton. We will see what it means in more detail in a few slides later. Okay, so that's what I can get by contractions. Now I want to give you component expressions, at least for the generalized Ricci tensor and the scalar curvature, which tend to be the things which appear in supergravity equations of motion. So we decompose the generalized vector and encoding the divergence operator into a vector x and the one from psi, and I'll write everything out in components. I give it here in this plus minus version because this is related to how things look upstairs on the courant algebroid. The one which appears in work on supergravity is the one with a plus, but you see the plus minus is only a relative sign between the symmetric and the antisymmetric part of this tensor, which in supergravity correspond to independent equations of motion. And then there is this generalized scalar curvature, which takes in generality this form here. And this here is now our new scalar invariant also written out and only depends on x and psi. Now, where does supergravity sit within this general setting? Well, supergravity is the case that we switch off the vector part and take the one form to be exact. And then we get precisely the expressions which have appeared in the literature on type 2 supergravity, written in the form of generalized Einstein equations. And our new scalar invariant is actually 0 in this setting, in a very trivial way because x is 0. Now, somewhat more interesting is something which I here call vector-deformed supergravity or generalized supergravity. This refers to a paper by Aratyunov and others, where some deformed version of the type 2 supergravity equations have been discussed. So this setting can be captured coming from the general case as follows. There are some conditions now on x and xi. X, the vector part of the divergence operator, is required to be a killing vector field. Xi and x contract to 0, and there's a relation between xi and x through the H field. And this then gives expressions which have appeared in this paper here. We also note that one can combine x and xi into a single vector x tilde, and this is how this is, I think, then mostly used in these papers. The new scalar invariant is still 0, but in a more interesting way. The vanishing of the new invariant is not precisely equivalent to the conditions which define this deformed setup, but very close to. The killing vector property implies that x is divergence-free, which kills this term, and this here is literally this term. Okay. Now, a bit more about this. Oh, that's interesting. Good. Still getting used to my iPad, I suppose. All right, now we are here. A bit more about this generalized supergravity setup, or the vector deformed supergravity setup. So the curvature equations that we saw are equivalent to a deformed version of the type 2 supergravity equations. How do these occur? Well, they are related to a deformation of the Green-Schwarz superstring on ADS5 times S5, called the eta-deformed integrable deformation. And this leads to some backgrounds, which are dubbed ABF backgrounds, which satisfy not the type 2 supergravity equation, but a deformed version. It's explained in the paper by Aratyunov and others. And a characteristic feature is that in these ABF time backgrounds, there's no dilaton, but a general one form. Now, at this point, we look back to T-duality for the first time, because one interesting fact about this ABF background is that they are T-dual to genuine type 2 backgrounds in a way where T-duality is formally applied to a situation where the torus action invariance that you have is not quite an invariance, but broken by a linear dependence of the dilaton on one of the otherwise isometric coordinates. So it's one of these settings where people have tried to apply T-duality in situations where the vector fields they're using is not fully a symmetry of all fields, and sometimes one finds something interesting this way, and they run then runs into these ABF time backgrounds which satisfy deformed supergravity equations. As a bit more context, this deformed Green-Schwarz superstring as a two-dimensional quantum field theory is scale invariance, but its Weil invariance is problematic. At least the standard argument for cancellation of the Weil anomaly doesn't work. And at least in the paper, it's then left unsettled whether this theory can be made Weil invariant, and therefore whether these are genuine superstring backgrounds or something outside of it. This as a side note. But I think it's interesting to see that this naturally falls into this generalized geometry setting. So let me now try to summarize where we are and give an outlook onto future work. So first, let's just take part 2 from the perspective of generalized relativity, leaving T-duality on the side. So what we have given is we have used a canonical Levi-Civita connection, generalized connection, to give a comprehensive curvature toolkit that people are invited to use. One question about this connection is there an additional condition which makes it actually unique? Is there some natural condition which really picks this? A priori, the construction is canonical, but since these Levi-Civita connections are not unique, there could be another canonical one, Well, then the difference between them would be a canonical tensor, meaning a tensor that you construct only out of the data that you are given. So it would it's not so clear what this possibly could be, but it would be interesting to clarify whether there's a more intrinsic or additional condition which really nails down this condition. Of course, also so far this mathematics, is this, we can also ask, is this connection physically distinguished? In particular, is it the correct one in the sense that the curvature invariants we can now construct are those actually found, say, in higher derivative terms in string theory. Still, even from a purely mathematical perspective, a follow-up project would be to construct in a systematic way curvature invariants. One would then complement this with also looking at geodesic deviation, and do things along the lines of general relativity, namely have a proper definition of what a singularity is, a concept of geodesic completeness, a concept of extendability or unextendability of generalized space-time defined in the setting. In the spirit of general relativity, one could then also move into physical dynamics. For example, the initial value problem. My coworker Cortez is, in fact, already for some time working on it, and with his student Oscar Schiller, he has, as a first step, developed what they call extrinsic generalized geometry. So this is the geometry that is induced on hypersurface within this generalized geometry setup. And that's a critical step in order to formulate and address the initial value problem for this, if you like, generalized relativity. Also, we have seen that the setting you have these general divergence operators which go beyond the dilaton, and there are now interesting questions how this really relates to physics. Good. Now, looping back to T-duality, finally, I would, of course, like to apply the results of part 2 and maybe further results to get some insight into these interfaces that we have produced by applying T-duality to killing horizons. We would like to know whether the interfaces are regular or singular from the point of view of generalized Riemannian geometry. And the full answer requires a full theory of curvature and curvature invariance. More physically phrased, can these interfaces be crossed by strings? Is this a cobordism into something? Or does one get stuck? Is this a kind of end of world? And is it just a formal thing that we have an interface, but in physical reality, there are actually then two solutions that we get by T-dualizing, which do not connect to each other and which each somehow end in a reasonable way. Also, one point that I mentioned that should be on the list is we would like to have an invariant which detects singularities in Ricci flat situations like a generalized Kretschmann scalar. So is there a generalized Kretschmann scalar? Well, actually, yes. Because if you look at contractions of two generalized Riemann tensors, then there's exactly one inequivalent non-trivial contraction that you can form, which is given here. It uses a generalized metric. And if you switch out H and the dilaton, it gives you the square norm of the Riemann tensor, aka the Kretschmann invariant. This is good news, but there's also some caution required. The potential issues is that T-duality invariance is not automatic. The reason is working in this generalized geometry setting with this so-called topological T-duality. There's a intricate kind of correspondence between the T-dual spaces, which allow to map certain data from one coherent algebra to the other, including rederiving the Buscher rules, including the dilaton shift. But it's not an isomorphism of coherent algebra. So we cannot bluntly say that everything that we construct on one side is automatically covariantly mapped to the other side. So it's currently under investigation. We're also aware that in the double field theory literature, there is a kind of no-go theorem for a generalized generalized Kretschmann scalar. We currently don't know how this relates to our results. It may be an issue double field theory versus generalized geometry. It might be something else. Currently, we don't know how to relate our results to these older results in the double field theory literature. further outlook to the future, I think it's a good strategy in generalized geometry to try to work with a generalized metric and a divergence operator, ideally without reference to a space-time metric B field or dilaton. We would like to establish or find out whether we can define our canonical connection without using the anchor map, because this would help with understanding how it transforms under T-duality, and hopefully we will get something reasonable and be able to establish that we can have really T-duality invariant curvature invariance. Question which I already asked before, are there additional geometric structures which makes the canonical connection unique? And so far we have, at least I don't understand too much about double field theory, but ultimately these formalisms of generalized geometry and double field theory are supposed to be related. There's lots of literature about this, and we would like to understand this. And but at the level of really full curvature tensors and curvature invariance, make the relation between concepts of curvature in both settings. And both settings, one clearly would like to have a concept of singularity, extendability, and so on. And based on such more formal developments, there are physical problems that we have partly touched upon. So we have these interfaces in relation to dynamical cobordism, which we would tackle. We have made plausible that you get tensionless strings as this interface. Is there anything one can say about the physics happening at these ends or interfaces by learning about tensionless strings? Long-term goal of mine is also to better understand the status of type 2 star strings. In fact, this relates to further things, because once you admit time like T-duality and go to type 2 star, and then use S-duality and then T-duality again, you get a whole network of type 2 string series in all possible space-time signatures. So this has been studied by Chris Hull, and Dijkgraaf, Heidenreich, Jefferson, Buffer have in fact argued that one should have dynamical transitions between string series in different signatures. But this is something that I would like to understand where this is, where this really happens. It's kind of the question: do these exotic string series really belong to string theory in the sense that I could have dynamical transitions from standard string series to these exotic series or not? And well, there's a lot of issues there. I think Ralph also has worked on this, and the status of these type 2 star strings is unsettled, and many of these aspects are a bit unsettling. So I think it's an open job to clarify how they really fit into our picture of string theory. Now, I think everything that I said is valid if you use T-duality just as a solution generating technique. But if one were allowed to take T-duality as a physical equivalence, then of course what happens at interfaces would tell us something about horizons and possibly about the physics of black holes. Thank you for your attention.
Thanks very much, Thomas, for this very interesting talk. Thank you. Other questions? No.